So thanks, Alicia, and thanks to the school for organising the event. It's a great privilege to be able to, I suppose, deliver an inaugural lecture here. What I'll try to do is, I suppose, give a broad overview of the research that I've been involved in over the years, and maybe try and dig into a couple of maybe core concepts and maybe key contributions that we made over the years. And I'll try and highlight the work that the various people have done over the years, and I hope I don't forget anybody as I'm going through it. So I wanted to start with some photographic evidence of my early tendency towards engineering. So I'm there on the right-hand side, and this was about when I was 7 or 8 years old. To explain, in our family, there's myself and I have 2 other brothers who are also engineers, and I think our mum won't mind me saying that our engineering tendency has come from our father. So that's my dad up on the roof. So dad is a primary school teacher. He was a primary school teacher. And he decided one summer that he wanted to build a holiday house in West Cork, between Ballyhale and Schull, which is where he comes from. And so we all went down as a family and built the house together. So myself, my 2 brothers, my mum and dad were literally labouring on the building site for the year. And that's my dad on the roof. That's pre-health and safety, and that's pre-risk assessments. I'm not on the roof. At that time, you had to be at least 10 years old to get up on the roof. But despite that, I didn't become a civil engineer. I decided I was supposed to become a biomedical engineer via mechanical engineering. And a lot of my work, I suppose, over my career has been in the area of multi-scale mechanics. Okay, so my title of my talk, I suppose, is Bridging Scales in Biomechanics. So in terms of understanding biomechanical systems, I suppose, you know, all of the functions that we have at, say, tissue and organ level are a consequence of all of the interactions that take place down at a molecular and a cell scale. Okay, so all of the interactions at this scale essentially govern your system performance up here. Okay, but I suppose what's really interesting about biological materials is that the environment up here actually influences adaptive processes down here. So they all drive cell behavior, and they drive a lot of molecular changes down at this level. So you have a really interesting feedback loop in biological materials, and they're really interesting to study. A lot of our work has been in the area of bone biomechanics. Okay, so why are we interested in bone biomechanics? So bone is one of the most exceptional materials that we have in either the natural world or in comparison to other engineering materials. It has high stiffness, high strength, and high toughness. Okay, so typically for materials, you are always, I suppose, finding a balance between stiffness and toughness. Okay, so down here we can have very stiff materials like ceramics, but obviously they're very brittle and they break easily. Or you can have quite tough materials, say like rubbers or epoxies, but obviously they have low stiffness. So bone is unique in the fact that it can achieve that balance of stiffness and toughness. We're also interested in bone biomechanics because it functionally adapts to its loading environment. Okay, so there's a natural design optimization that takes place. And this was first observed by Julius Wolff. Okay, so Julius Wolff published a paper in 1892 where he observed that when you look at the internal structure of a bone here, what you see is that all these trabecular struts here, when you analyze these from an engineering perspective, it's kind of a beam-like structure. All of those structures align to the direction of the principal stress. Okay, so you get a structure that has been in some way optimized for the particular loading environment that it experiences. Okay, and the result of this is that your bones are constantly adapting and optimizing for the forces that they experience. Okay, so what you see is that athletes would typically have much higher bone mass than a regular population, and this is kind of demonstrated here, where you would see in professional tennis players, in their dominant serving arm, they will have a bone mass that is probably 20 to 30% higher than their non-dominant arm, and that's from the constant repeated load that they experience. The opposite is also true. If you're not doing load-bearing exercise, you will lose bone mass, and that's a big problem for astronauts coming back from space. So they have a loss of bone mass, and they need to recover it when they return. We also study bone biomechanics because we have a substantial number of fragility fractures every year here in Ireland. So our bone mass is constantly being renewed, and typically our bone mass peaks at about the age of 30. Once we go beyond the age of 30, we gradually lose bone mass down into our later years. And with this, we start to experience an increased risk of fracture. Okay, so what you might see is for a strong, healthy 30-year-old, you see a very healthy bone mass and healthy structure here. But as you go into your later years, you can develop what's called osteoporosis, which is a disease that many people will be familiar with, which literally means porous bones. So you start to lose these structures in your tissue here. Okay, and with this, we can, I suppose we have approaches to clinically screen for osteoporosis. Okay, so going for a DEXA scan essentially, I suppose, measures the density of the tissue, and it stratifies you in terms of, you know, whether you have healthy bone mass, an osteopenic bone mass, or an osteoporotic bone mass, and that will affect your, you know, maybe how you might treat that disease. And this is really important because about between 1 in 4 and 1 in 3 people will die within 12 months of a hip fracture. Okay, so for elderly people having a hip fracture, it's a very debilitating thing to happen, and you get a lot of secondary effects happening from the effect of that hip fracture that can take place within that year. So we're very interested in studying this material, and in terms of, I suppose, understanding again, and usually we have, you know, exceptional properties and a material that has very high strength and high toughness, and that all arises from the hierarchical arrangement of the tissue. Okay, so bone is a very complex structure. Okay, so it's arranged across a number of different length scales depending on what scale you're looking at, and ultimately it's made by 2 fundamental building blocks. Okay, so the 2 main components of bone are collagen and hydroxyapatite mineral, or calcium. Okay, so collagen is the, I suppose, it's the building block for all of our connective tissues. Okay, so collagen makes up a lot, or the vast majority of our soft tissue. And when the body needs a stiff and a strong tissue, what it does is it basically mineralizes that collagen structure. Okay, so you have calcium, and that's why you need calcium for your bones. You have calcium minerals that come into this collagen structure, and they give bone its stiffness. But I guess with this material, I guess the complex arrangement of those 2 components and how they're arranged up through this architecture makes it really difficult to understand how bone actually behaves as a structural material. And that's really what a lot of our research has focused on. Okay? So I'm going to come back to some of those concepts, but in terms of, I suppose, the start of kind of this journey of you know, being able to understand bone biomechanics, it started in my PhD. And as Leisha said, I started my PhD, well, I did my undergraduate degree in mechanical engineering, and I also did my postgraduate degree in mechanical engineering in the area of composite materials. So I did my PhD under an ERCSET scholarship back in 2007, and I worked with Professor Conor McCarthy. So Conor was quite early in his career at that stage, had great enthusiasm for research, and it was great to work under. And we were working in trying to understand how, I suppose, how composite materials behaved in terms of their micromechanical behavior based on their constituent materials. Okay, so for a composite material, what you typically do is you combine a stiff fiber material with a more compliant polymer matrix. Okay, so and that's similar to bone. You're combining a stiff material with a soft material to give you that balance of properties. So they come together through a curing process, and you get kind of a composite laminate, which are used in a lot of different structural applications, okay, such as aircraft and wind turbines. And as engineers, I guess what we like to do is we like to take a very structured and rigorous approach to actually understanding material behavior. Okay, so one of the main things in an engineer's toolkit is doing uniaxial tensile testing to understand how material behaves. And we have plethora of standards that kind of define the process to actually, I suppose, characterize materials at that length scale, right? And what you typically get out of this is a stress-strain curve, okay? So, and from that stress-strain curve, we can define, say, different engineering properties that we're very used to dealing with. You can have your Young's modulus here, you can have your yield stress here, and you can have your ultimate strength here. And I guess in engineering materials, we're very familiar with dealing with nice linear behavior, so getting something that behaves according to Hooke's law, where you get a nice, easy Young's modulus. But as you start to, I suppose, go beyond that linear behavior, what you see is in your stress-strain curve, you start to get this non-linear behavior here, where something is starting to happen in the material that is causing, I suppose, a drop-off in stress. And generally what's happening is that you're seeing damage accumulation in this part of the curve. But at this, I suppose, scale of observation, you don't actually understand or know what's going on, okay? So if you look at these types of materials in more detail, what you see is that at, say, apply level, okay, so here we're looking at a transverse cross-section here, so the circles here are your carbon fibers which are coming out of the page, and the darker material is the polymer matrix. And what you'll see is that you'll start to see things like transverse ply cracks happening, and those cracks will have started from debonding here between your two fiber components. And in this material, your fibers here are about 7 to 10 microns in diameter. Okay, so together, all of these, I suppose, damage mechanisms start to accumulate during this phase of the stress-strain curve, and they ultimately lead to failure through, I suppose, reaching a saturation or a limit, and that will lead to an overall crack within the material. And that's kind of how any material will ultimately fail. So my PhD was really trying to, I suppose, develop micromechanical models to predict that process, okay, to try to better understand why material failure happened in composite materials. So the approach that we took here is through what's called multi-scale modeling. Okay, so the general approach here is we define what's called a representative volume element of a material. Okay, so here where we have our fibers and our matrix represented, we use an approach where we're actually able to, I suppose, resolve local variables within this picture here. So what we do is we break it up into small little parts, so we discretize it into a finite element mesh, and for each of these little elements that we have here, we're able to define their behavior based on some kind of relationship. Okay, so for linear behavior, we can use Hooke's law, and that can define the relationship between those two springs. Okay, and if we want to get more complex behavior, we can use a nonlinear term, and that can give us, I suppose, allow us to predict things like fracture. Okay, so we solve that problem, and we, I suppose, resolve, the local stress that would be happening in the microstructure under a particular loading condition. And this is kind of giving you a picture of what's happening in that structure under a load that's happening at a much higher length scale. And from that, we can basically average the components or average the stresses in that structure, and we can kind of predict our typical material properties for this type of material. Okay, so in terms of my PhD, I suppose I implemented a couple of damage models that really were able to capture these processes. Okay, so we looked at this type of a material element being stressed under transverse tension, and what we predicted, or what we were able to predict, was, I suppose, the fracture path that happened from that type of loading. And you can see it's recreating the kind of damage mechanism that you saw on the earlier slides. We also looked at this under compression. Okay, so under transverse compression, you get the material being compressed horizontally, and you get these fracture paths happening through kind of a yielding in the matrix. And what we can also do from that is we can predict, or we can actually capture, say, the overall stress-strain curve. Okay, so we can start to predict how material behaves based on this microstructural component. And we published, I suppose, a series of papers at that from a PhD, and they turned out to be very well cited, and they, I suppose, gave me a perspective on how to look at problems in biomechanics, okay? And when I finished my PhD, I looked at, well, what do I want to do next? And I saw an advert, and what I wanted to do, I wasn't sure that I wanted to stay in, say, kind of comms and materials, which was kind of an aerospace application. Not a lot of jobs around in Ireland in that. So I thought about moving over to biomedical. And I saw an advert for a postdoctoral fellowship in computational mechanobiology. And I didn't know what mechanobiology was, but it was a project around predicting mechanical stimuli that bone cells experience under in vivo loading. So that didn't sound too bad. And the experience that Leisha was looking for was very much aligned with the skills that I'd learned during my PhD. And this project was funded by the European Research Council, which was obviously, I suppose, beneficial to me in terms of learning throughout my career. So I joined Leisha in, I think it was June 2011, and took on a postdoc in NUIG, as it was at the time. And during my postdoc, I suppose I came from mechanical engineering into a completely new field. So very much a change of disciplines, but I suppose I managed to adapt to the field of bone biomechanics and mechanobiology, and I suppose worked in a lot of different areas that I suppose kind of gave me a broad understanding of different aspects of biomechanics during those years. So I developed some early models in kind of multi-scale modeling around tissue biomechanics, worked in the area of cellular mechanosensations, understanding how cells behave on different substrates, and also worked in trabecular bone marrow mechanics. And for that I visited Glenn Never over the University of Notre Dame, which was a great international experience. And also during that time, I guess we were based here in the building, up in the research space. We had a great group. Many people in this research group, or in these research groups, would be familiar faces. Okay, so people like Emer Dolan, Will Ronan. We had a lot of fun. This is a picture from the National Bioengineering in Ireland Conference, which has a fancy dress every year. I'm in the back, not dressed up, because as many people know me, I don't do fancy dress. And we've had a lot of, I suppose, great friendships built up over that. And these are different pictures from different weddings from all of that group. So it was a great time to get to know many people. I was then appointed as a lecturer in biomedical engineering in 2015. And as Leisha said, I ended up teaching tissue engineering, which was a little bit of a hospital pass from Peter, who was head of discipline at the time. But I got through it. But I joined in 2015, and biomedical engineering was a really small discipline at that time. It was really, it was Peter McHugh, it was Leisha and Pat McGarry, really, when I joined, were the kind of core members of the discipline. And I suppose I joined in 2015, Will Ronan joined soon after that, and then Emer Dolan, so we started to grow. And that was based around a lot of growth in student numbers. So, you know, just before I joined, we were looking at 20 to 30 students, and we went from, you know, that kind of number up to numbers of about 80 to 90 students in fourth year in a few years later. So that led to a lot of growth in the department. But it also meant that things were extremely busy in terms of teaching, in terms of supervising students, and in terms of other things going on in the discipline and in the school. But I started to build my research group, I suppose, from that time. And I'm coming back to this. So we started to look at the area of bone biomechanics. And in terms of this area, I guess a lot of research in bone biomechanics at that time was in the area of osteoporosis. Okay, so osteoporosis is by far the most studied bone disease that there is, and that's for good reason. But with osteoporosis, it's very much driven by the structure of the tissue. So if you get a certain loss in bone density, or if you lose a certain amount of your structure of the tissue, you almost get a corresponding increased risk in fragility. So it's very much linked to structure. So from a biomechanics point of view, there weren't too many interesting questions around osteoporosis. So what I suppose came upon and it was through, I suppose, some meetings that we had with a group in the hospital through Tim O'Brien and Cindy Coleman and Leisha. They were starting to look heavily at the area of type 2 diabetes. Mainly around, I suppose, behavior of cells in type 2 diabetes. But what they were starting to identify and what was starting to come out in those years is that there's also an increased risk of fracture in type 2 diabetes. Okay, so there can be up to a 3-fold increased risk of hip fracture if you have long-term diabetes. But what's interesting about this is that this increased risk of fracture is not associated with any loss of bone density. Okay, so whereas osteoporosis, you lose all this bone structure here, in type 2 diabetes, you present as a perfectly healthy bone mineral density. So what that means is that the bone matrix or the bone tissue itself must be impaired in type 2 diabetes. So came up with the hypothesis and started reading into this, and Owen Parle did some work early on in this. And when we read into this, one of the leading hypotheses at the time was that the increased risk of fracture was due to the development of what are called advanced glycation end products. So these are basically small little molecules that come in and create cross-links between the collagen molecules that are there. So the idea behind that is that they essentially stiffen the collagen network, which leads to more brittle behavior. But there was, while it was kind of well hypothesized, it was never really, I suppose, linked to actual mechanical behavior. So I wrote a project basically trying to probe this relationship. So the hypothesis of the project is that if we can measure the relationship between these cross-links and the mechanical behavior of the tissue, we should be able to come up with a better way to assess fracture risk in type 2 diabetic patients. I was lucky that that project was funded initially by the Irish Research Council through their first laureate scheme, and it was then funded by the European Research Council starter grant. So what that allowed me to do was recruit a really great team working in the area of both experimental and computational biomechanics. So recruited Jenna, Maddie, Hamid, Jessica, Matab, Marissa, and also Wahaj, who joined us recently. And we started to look at both kind of the experimental and we started looking at the how the tissue behaved mechanically, and also developed computational models around tissue behavior as well. Okay, so some of the work that we did, we looked at getting femoral heads from the hospital, so people who were undergoing hip surgery. Generally, the femoral head is thrown away, so we started collecting that tissue from these different patient cohorts. And Marissa Britton tested this tissue and was able to characterize mechanical behavior. What she found is that we really didn't see any link between that cross-linking mechanism and the behavior of the tissue. So we had to look maybe a little bit deeper. And Jenna Monaghan did an animal study, and this was supported by Jessica Schiavi. And she looked at, I suppose, a diabetic animal model and did these really small-scale tests on animal tissue. So compared to the structures that Owen is dealing with, we're down at the level of a couple of millimeters here, and started to look at the properties of these tissues in this type 2 diabetic animal model. And what she did observe, she did see, I suppose, changes in deterioration of mechanical properties, but again, she found it very difficult to actually relate that to the AGE content, which was what we were trying to correlate to. But what we identified was really that there's a multitude of changes taking place in the tissue during type 2 diabetes, and that it's really a much more complex disease that actually contributes to that increased risk of bone fragility. And I suppose to really understand that, and I suppose what's difficult about bone tissue is that you really have very limited, I suppose, techniques to really measure properties down at these length scales, and it's these components that kind of drive tissue behavior. So we developed, I suppose, computational models around some of this behavior. Okay, so just looking at this in just a small bit of detail. So this is a microstructure image of bone tissue, and you kind of see a similar structure to some of the composite materials that you see here. The little small fiber-based structures are these mineralized collagen fibrils. So these are collagen molecules, again, with your mineral crystal that comes in here. And then the other piece is kind of a mineralized matrix, okay? So we looked at developing, I suppose, a couple of models, and this was work that Madi Tabakal did. So Madi was a postdoc that joined me from Iran, and he looked at developing coarse-grain molecular dynamics models for these materials, for understanding these collagen fibrils. Okay, so whereas I mentioned that the approach with finite elements is to use the idea of Hooke's law and linear spring to describe behavior. Molecular dynamics, I suppose, considers each of these materials as a coarse grain or as a kind of a bead-based structure, and it defines, I suppose, the relationship between these grains as a kind of a bond curve. Okay, so you have, I suppose, a difference, a kind of a U-shaped behavior depending on the distance between these molecules. And what Madi did is he developed a lot of, I suppose, really elegant models around behavior here. And the first thing he identified is that when you introduce mineral into a collagen fibril structure, you get a shortening of this mineralized collagen structure. Okay, so you introduce a residual strain in the structure just by introducing the mineral itself. And he then looked at these simulations under axial loading. And what he found was that when you introduce mineral, you get a much stronger response from the mineralized collagen fibril. And he was kind of one of the first to identify that the real function of, I suppose, these minerals in the fibril itself was not just for stiffness, but they also provide a very strong bond between collagen fibrils. And they enable a lot of energy dissipation because of that. I'm going to move on a little bit quicker here. He also looked at a system where he brought these mineralized collagen fibrils together and he included them in a kind of a mineral matrix. So this is kind of a mineral system here, and he did the same types of simulations on these. And one really important thing that he had identified here is he identified that when you, again, introduce these two systems together, what you find is that the fibrils in the structure want to contract. Okay, so they want to shorten due to the intrafibrillar mineral that you have, and that leads to very large residual stresses in the system. So you get very large compressive stresses happening in this system due to this shortening. So on the order of about 100 megapascals. And what he found was when you load these under tension, so these are some of the simulations under tension, you actually find that these residual stresses play a big important role in actually contributing to the strength of the material. And also he identified, I suppose, some other mechanisms like fibril bridging, which is a kind of a toughening mechanism at this scale that essentially bone can use to, I suppose, again, increase its energy dissipation capacity. Okay, and it was exciting to see that this same, I suppose, this same residual stress was observed experimentally around the same time. And this idea of a kind of a compressive pre-stress is actually a concept that we use in engineering. So pre-stress concrete would use this concept where you kind of pull the material together to enhance its behavior. And I guess I'm going to just move on from this, but what we found with these models was very much that bone as a tissue will almost design itself to optimize its behavior, and you'll see a lot of really elegant features that optimize behavior. I suppose that we then observe elsewhere in say engineering structures. Okay. In terms of other models, I suppose we linked some of these models then through, I suppose, a more traditional finite element approach. This was work by Hamid Alajani. Okay, so he just did larger scale models where he also started looking at fracture behavior between, say, mineralized collagen fibrils and this matrix, and he also started predicting some behavior at larger length scales. Okay, so I'm going to move on, and I guess we're kind of continuing this work through Ahaj and also through Gabriel Conahan, who are doing further experimental characterization through a new nano CT system that we have here in the School of Engineering. So I want to talk just for a little bit about our work in the area of functional adaptation. Okay, so I mentioned that bone is a structure that can naturally, I suppose, accommodate or naturally adapt to its loading environment. And this was first observed through Wolff's law. So Conal Quinn did his PhD with me, and he did a lot of work to develop models around these types of concepts. So he developed models that would, I suppose, look at that optimization process and how bone actually optimizes its structure. So these are generally based on, I suppose, minimizing what's called the strain energy density in the structure. So the models that he developed, if he applies these models, if he applies simple loading conditions under these models, what you find is that the algorithm will adapt and find the most efficient structure that it can find for this. So under simple uniaxial loading, you just get a straight beam or a straight strut. If you put more complex loading on this, you start to get a more elegant kind of a truss structure that you, again, more typically see, or that you more typically see in this type of trabecular network. And we've kind of built on these models, and Conal did a huge amount of work in developing these models, and we've used these in a project recently with Matt Tabb, who's also been working with me for quite a number of years. And we've been looking at the area of cranial growth. So one of the issues in the development of the cranium is you can have a condition what's called craniosynostosis. So this is where you have premature fusion of the sutures in the cranium. So anybody that has young children will know that their head is really, really soft in the first couple of years of their life, and it gradually develops. But it needs to be soft and compliant so that it can grow and expand over time. So Matt Tabb has applied these models recently, and again integrated some of Conal's growth models and developed them further to predict I suppose, predict cranial growth in terms of how it's mechanically driven. Okay, so for a healthy skull, you can see that you get a nice regular shape here. But in these other models, what she's done is she's looked at where you have early fusion of one of the sutures. Okay, so here you have an early fusion of the sagittal suture, and what you start to see is an asymmetry in how the skull develops. So you get I suppose, an uneven or a buildup of pressure in these skulls that are, I suppose, overly constrained, and that leads to kind of a deformity in how the skull develops, and that's exactly how craniosynostosis develops. And from the models she developed, she's actually able to get a very good correlation with, I suppose, how these have been observed to happen clinically. But like that, it's kind of by integrating the kind of the mechanically driven component of cranial growth. Okay, so Owen included a few detours along the way, and I'm also going to talk very briefly about my medical technology research. So I guess as well as bone biomechanics, I've also done a lot of work in the area of medical devices. And working in a university in Galway, it's hard not to work in the area of endovascular stenting. So in Ireland, we have obviously a huge medical device industry, and we have, I think in Galway, we manufacture over 8 million stents annually. Okay, so Ireland manufactures about 80% of the world's stents that are produced. And I suppose a stent is a device that is used to treat atherosclerosis. So where you have a buildup of plaque in your artery, you come in with an endovascular stent. It's deployed minimally invasively. It opens your artery and it restores blood flow to whatever vasculature you're dealing with. And I've done, I suppose, quite a number of projects in the area of cardiovascular stents. First project, and my first PhD student was Ciara McKenna. So she worked in the area of wire-braided stents. So wire-braided stents are manufactured kind of using a kind of a textile-based machine. Okay, so this is a wire braider that brings nitinol wires together and creates this structure for a stent that can be, I suppose, very useful in how flexible it is. And she was also looking at polymer coverings for these stents. Okay, so the polymer covering was to provide a better barrier against the vessel wall. And she developed, I suppose, very advanced computational models to describe this behavior. And I suppose by developing these models, she was able to, I suppose, predict, how the various components of these stents and their design. So depending on what maybe braid angle you would use, or depending on what cover thickness you might use, she was able to predict the mechanical response of those devices. And she was able to, I suppose, validate that against some of her experiments. So this is, again, one of the I suppose, benefits of these braided stents, where you have this really good kink behavior, and her models match that very nicely. I suppose soon after I recruited Kira, we got involved in a Horizon 2020 project in 2017, and this was on in silico clinical trials. And this was around developing, I suppose, computational models to predict the performance of bioresorbable vascular stents. So we were part of a project here that, I suppose, brought together a consortium from across Europe. And this was myself and Will Ronan were the PIs in this project. And it really gave us an insight into, I suppose, a lot of the other expertise that was there in Europe to kind of deal with this problem. And it was our kind of first exposure to, a European consortium. We, I suppose, got involved in this consortium at the proposal stage. And one of the big things that they wanted from us was to see if we could get Boston Scientific on board. Okay, and we're actually a very, very lucky in Galway that we are a gateway to a lot of the companies that are here. For this project, we recruited 4 people. We had Owen Parrell again, we had Kate Polokrasna, who were the postdocs on the project, and both Will and myself co-supervised Confiuta and Ali, who I saw there earlier. So the overall idea of this project was to, I suppose, develop and integrate computational models to predict the long-term performance of these bioabsorbable stents. So we worked very closely with Politecnico Milano, who were, I suppose, really leaders in terms of developing some of these models. This is a deployment model for a coronary stent. And other partners in the project were developing things like fluid dynamics models, okay, so to understand how did the fluid behave once the stent was implanted, and also drug delivery model. And our role here was in the area of degradation. Okay, so we were predicting the degradation of these devices. And this is some of the work here that Confiuta has done. So we were looking at long-term degradation studies of these stents to see, well, how do they actually break down over time, and how does the mechanical behavior change over time. And Con also developed kind of models around degradation as well that was able to capture that behavior. And then Ali kind of looked at the lower scale. So he was looking at micromechanical models of this polymer material as well, and started developing approaches, I suppose, to be able to predict that. I suppose in parallel, and once we had kind of some experience of kind of Horizon projects, I then led a Marie Curie doctoral network. And I should say that, I suppose, Peter McHugh, I suppose, initially kind of assembled some of this network, almost back before I had started. And I worked with him on this project, on this proposal, for a number of years. And I think it took us 4 goes to actually get this project funded. So by the time we had it funded, we had lots of meetings, lots of different iterations of the proposal. But we brought together a consortium that was kind of looking at different materials for medical implants. And with this, we recruited 12 early stage researchers, okay, so across this consortium. And I guess I recruited 4 PhD students here in Galway, who worked, I suppose, between ourselves and some of the companies in this project. And I also recruited Dr. Eva Barrett as the project manager, who's just been outstanding, and she's still working with us today. And I guess we looked at a number of different areas in this project. Martina Bernini and Swati Nandan looked at the area of femoral popliteal stenting. So Swati was supervised by myself and Emer. So Swati looked at developing, I suppose, both in vitro models for stent deployment. Okay, so developing cell-based models to be able to, I suppose, characterize how you can deploy a stent in vitro, and also looking at cadaver models to understand, I suppose, the biomechanics of this femoral popliteal artery. So this is the artery that runs behind your knee, and that artery has very large deformation. So you have a lot of problems with stent fractures in this artery when they're implanted. So Swati did a lot of cadaver work to try and understand the biomechanical forces that were acting on this artery. And Martina brought that together then with computational models of the same artery. Okay, so this is models that are reconstructed from the in vivo imaging that Swati did, where she's actually looking at the deformation of the artery, and she was also able to predict the actual behavior of a stent in that artery as well. I'm going to move on to some of the other work that we did in this consortium. We worked a lot in the area of magnesium bioabsorbable materials. Okay, so in terms of, I suppose, some of the issues that we have with stents, when you implant a stent, you obviously are implanting a very stiff structure into an artery, which is usually very compliant. And what you can get is you can get a response here where the artery actually re-narrows after you implant the stent. It's called in-stent restenosis. And if that happens, you have to re-expand the artery, or you have to re-stent the artery. And it's very common for people to have to undergo 2, 3, and 4 procedures to actually keep getting their artery reopened with stents. And you also have issues with some permanent materials in orthopedics where you have I suppose, permanent materials that are embedded in your tissue for extended periods of time. So we worked a lot in the area of magnesium as a bioabsorbable material. So for this, we partnered with Alex Kopp. So Alex Kopp has a company in Germany, in Aachen, called Miotech. They were a small startup company, but they've grown a lot since we partnered with them. And they've spun out a company called Medical Magnesium, where they're actually producing magnesium implants for medical devices. And in this company, I suppose they have a lot of capability and expertise in producing magnesium as a material. And we partnered with them on a lot of projects to try to understand how magnesium actually behaves in terms of its corrosion behavior. Okay, so magnesium, the process through which it degrades, is essentially corrosion, which is similar to what you see here on this steel frame structure. And obviously, when you have kind of a surface corrosion mechanism like this, what's really hard is to design for that process, because you get kind of these localized pits that create a lot of issues when trying to design something mechanically. So Kirsten Van Galen worked on a kind of a project looking in a lot of detail how these nice engineering dog bone specimens corrode. Okay, so you can see the corrosion surface here. And she did a lot of work to characterize these using CT scanning to understand behavior. Conal Quinn worked a lot in the development of corrosion models. Okay, so this is a surface corrosion model to, I suppose, predict that corrosion process taking place on the surface of that material. And they brought that together in a paper that looked at the application of a new coating system that would essentially, I suppose, reduce the rate of corrosion in these systems. So this is called a plasma electro-oxidation treatment that can actually inhibit that corrosion and enable the implant to last much longer than it's designed to, or than it can achieve with a non-coated sample. And we also had a partnership on, I suppose, coating these structures with silk fibrin, which is what Benedetta Isella has worked on. But that's been a really successful partnership for myself in terms of kind of collaborating with Alex. And as BioImplant finished, we started to, I suppose, propose an entirely new project. So we've just started another doctoral network that is developing bioabsorbable metallic endovascular devices. Okay, so this project was, I suppose, led in terms of proposal preparation by Eva Barrett. So Eva stayed on with me and developed the proposal for this network. And what we have done is, I suppose, assembled another network across different partners in Europe that can essentially bring together the expertise to produce materials for endovascular devices, that can bring together capabilities to design new endovascular devices, and also we have a couple of clinical partners to do animal work for this. Okay, so we've just recruited 15 doctoral candidates for this project. So this is a picture from our midterm review just a couple of weeks ago, and we have a number of students that have just started their PhDs between ourselves and some of the companies on the network, and it's managed by Sinead Mellett, who's joined us recently. I'm also going to mention just a few other different collaborations. So Fatima is co-supervised between myself and Peter, and she's working on understanding grain structures in magnesium. We've also had a long-standing collaboration with Lifelet Medical, with El Sanders. So Bobby Whiting did his PhD with myself, and also working with El through Lifelet. And this project has led out into a DTIF program, which Ali worked on. I see Koya there who also worked on it. And we've also just started a project on a digital stent, which is led by Derek O'Keefe and Adnan Elahi, where we're trying to integrate sensors into these stent-type devices, and we're working on some of the modelling. And Andrew Simpkin is also involved in that on the data side. But he collaborates with everybody, so. Okay, so I'm nearly finished, and I'm very conscious of time. So I suppose just maybe to wrap up, and I suppose that's kind of an overview of research, and I suppose I've obviously taken on a lot of different roles in my time, and I started as the interim director of the Institute for Health Discovery and Innovation in the past year, and this has been hugely rewarding as an experience. And we've had a really busy year. We've, I suppose, established the structures of the institute. We obviously had a big institute launch, and I suppose we're just starting to kind of gather our membership, and it's been great to have, I suppose, such really good engagement from all of the people that work in this space. In terms of, I suppose, in particular, I suppose, we've such a fantastic infrastructure here in the university in this area. And I was at Terry Smith's retirement yesterday, who kind of spoke around, the start of all that, and kind of, getting PRTLI funding, getting money to start buildings, to, start different programs and different research groups, which have really led to the overall kind of ecosystem that we have in the university. So it's been really great to have that role, and it's also been really great to work with people like Elaine, work with Steve Griffin, who is just one of the most operationally efficient people I've ever met, and also Anne Ryan, who's been fantastic in terms of her advice for this. I also want to acknowledge colleagues in engineering, and in particular in biomedical engineering. And I guess I mentioned at the start that we were a very small discipline, and we've grown to something really large, and it's been an outstanding success story. And I think I want to commend, I suppose, all of the new PIs and the new faculty that have come in and have been really successful in their own right, getting new ERC awards, getting Royal Society awards, getting new doctoral networks. I want to acknowledge in particular Will and Emer, who kind of joined at a similar time to me. We were always kind of co-supervising or co-chairing different meetings, so we've been kind of there along the way. And I also want to obviously acknowledge Peter McHugh, who kind of, I suppose, was responsible for starting a lot of this. And also acknowledge, obviously, Leisha's contribution here. So Leisha has been, I suppose, a stalwart in engineering since she's been here, and obviously she's been, I've worked very close with her over the years. She's been a fantastic mentor to me, and I suppose what I've learned from Leisha, and what I learned very quickly, was it's not just about research. You have to, put in the effort in every other aspect of the job, and Leisha showed that, whether it was around being representing on an internationalization committee, on a marketing committee, as a program director. It's the same level and the same standard that's required, and that has, I think, really precipitated down through the building. So Leisha and myself have, and I still come to Leisha for advice, and we discuss things, and we've only had maybe one big argument, which had to be settled in a swimming pool, which you can ask Leisha about. You can ask Leisha about afterwards. And obviously thanks to all the other wider colleagues in the School of Engineering. And most importantly, I want to thank my family. So thanks very much to Mags. Obviously it's been an incredibly busy year and several years, so Mags is always there and is a lot of support to me. And thanks to obviously all our families, but also both our parents who were there to support. Sarah, who is here, she was giving out earlier, so hopefully she's not been too bad. Okay, I think that's it. Thank you.